Hello, everybody. Welcome back to Question Field, the place where you ask the questions and we field them. I am Brian.
And I'm Campbell.
And we are diving into something pretty simple today. Pretty simple. Quantum computers. Pretty,
Notoriously easy to understand.
Yeah. I mean, we were going to brush over this episode. We figured all of our listeners already knew this backwards and forwards, but we figured, there's probably one or two people out there that haven't caught up yet. So we thought we would take the time. No, but for real.
So obviously, yeah, they're actually very difficult to understand, to the extent that, Feynman said famously, nobody understands quantum mechanics, and quantum computers are sort of applied quantum mechanics. So I suppose, according to him, nobody understands them either.
And I mean, forget quantum physics, like computers for me, like they are these magic boxes. I have a vague understanding of how they work. So let's add quantum physics to that and see how it goes.
Okay.
Campbell, this is actually for you a little close to home, is it not?
It is a subject very close to my heart. Somewhat of a love-hate relationship, of course. But yeah, so I'm doing my PhD on topics that are, within this field. So I deal with these ideas from quantum computing quite regularly. And, not all aspects of quantum computing, obviously. It's an incredibly broad topic. But certain things within the field I focus on in my day job.
Yeah.
So it's certainly very exciting to talk about.
Yeah, and it's a privilege of mine to get to ask you some of these questions. So here's how we'll start. How about I give you my impression of what a quantum computer is and or does, and then we take it from there.
All right, sounds good.
So let's start with computers, as I understand them. You have transistors that work as like logic gates, and you have all these different gates that you combine them in certain orders, and you can spit out computations. Go figure, a computer that does computations, right? And that's great. And we've gotten to a point where we can do that very, very fast.
Yeah,
it's still, so computers can do really complicated math really well, but there's still some computations that are just beyond what current computers will ever be able to do in a meaningful time frame. And by meaningful, let's say like a human life, right? So I think one area is like busting cryptography, right? For messages or banking, whatever. And so my understanding, sort of the process, for a normal computer, where a normal computer has to go through every iteration of a certain calculation, quantum computers, where you have something that can be in between states, means that you can speed up those calculations and make them more efficient, and take something that would take many lifetimes, you could do that much quicker.
In a matter of minutes.
Yes.
Yeah, that's the idea. Yeah, so there are a few things in what you said that we could dive into a little more deeply.
Yeah.
The first one is the way that classical computers work. So classical is the opposite of quantum. It's the word that we use to describe the world that we know and love. So, for example, a classical bit is a variable that can take two values, either 0 or 1. Mm-hmm. That's the sort of maths behind the way computers work, is that they take bit strings and apply gates to those bit strings, so logic gates.
Right.
And the way that they are usually represented in a computer, as you said, is through transistors. So a transistor can either have current flowing through it, or it can have no current flowing through it. Mm. And those two states represent the 0 and the 1 of the bit. Mm. And so logic gates take in, usually I think for a classical computer, they either take in 1 or 2 input bits, and then depending on the state of those input bits, whether they're zeros or ones or a mixed, 0, 1 or 1, 0, they produce some output bit, which can also be 0 or 1. Mm. So, for example, you could have just a bit flip gate, which if you input a bit which is in the 0 state, it flips it to a 1 state, and vice versa. If you input a 1, it flips it to a 0. And you can also have the AND gate, which takes in 2 bits. And if the input bits are both 1, the output bit is 1. And for any other input, the output is 0. Okay, so you've got all these operations that you can do on bits, and you take in some bits and you spit out some other bits. And those are, you can, as you said before, you can string these logic gates together into some sequence, and that is effectively what an algorithm is. It's a series of operations that you do on bits to get certain outputs and perform certain computations. So that's the model of computing that we have in mind with classical computers. And specifically, you might worry that, well, there are sort of so many different operations and computations that we can do on series of zeros and ones. Aren't we going to have, an infinite number of things that we might need our computer to do?
Right.
But it turns out that you only need a certain finite set of these logic gates. And from that finite set, you can do any computation that you like. Anything that you would want to do with, transmitting audio and visual files over the internet, or I don't know, playing a game or something like that.
Right.
So that's really useful. So that is called a universal gate set, because it can do anything by just stringing these logic gates together.
Sounds fancy. Sounds fancy and useful.
Absolutely. Yeah, and it's very useful. And there is an analog within quantum computing. So we'll get to what this means, but something, that we are kind of interested in the field is how can you achieve all of the universal, or a set of universal gates within a quantum computer. So that's also very nice. The fact that you have a finite set of gates of logic gates that you can apply within a quantum computer, and that we can achieve these. Well, we'll talk about this, but the hope is that we can achieve these. Okay, so that's classical computing. The next thing you said was quantum computers kind of represent information in this sort of middle ground state. Maybe you've got, maybe in classical computers you have zeros and ones, and in quantum computers you have things that are sort of in between zeros and ones, right? So yeah, that's exactly right. That's called superposition. And it's not actually by itself that strange. You can think of this very naturally by if you replace all of your zeros and ones in a classical computer with little arrows, and those arrows can point anywhere in 3D space.
Right.
So they have a fixed length. The arrow is always length 1, if you like.
Sure.
But it can point anywhere on the surface of a sphere. So the way I like to think about that is that you can think of the sphere as the globe, the Earth. We are not flat earthers here. I think we've said before, actually. So the little arrow can point anywhere on the globe. So, for example, it can be pointing at the North Pole, at the South Pole, along the equator, something like that.
Right.
And that is the mathematical representation of a quantum bit, or a qubit. So if you take the words quantum and the words bit and you smush them together, then you get the word qubit. So QUBIT.
Probably saves a lot of time at your meetings.
Yeah, absolutely. So we've got this idea of a qubit. So the little arrow is the quantum equivalent of the 0 or 1 in a classical computer. The way that a quantum computer works then is to take in a bunch of these qubits in some input state. Maybe all of the qubits are initially pointing to the North Pole. Then you apply a set of logic gates, of quantum logic gates, on these qubits. Now, we can talk a bit more about what those gates actually look like, but there are some operations that you can do, some transformations of the states of those qubits. And then, after you do all of those logic gates, you need to get some information out.
Right.
So the way that you get information out of your quantum computer is you do measurements. So measuring qubits is the sort of extra ingredient that you need on top of the logic gates to be able to do your computation. Okay, so that's all that is. That's all there is for quantum
easy
computing.
peasy. Easy
Yeah,
peasy,
it's so easy, right? You prepare some states, some qubits in a particular input state, you do some logic gates, then you measure them, and that's it. But obviously, we need to understand those three ingredients much more closely.
So let me ask you. So we were saying how these gates in a classical computer are transistors, and you either have current or you don't have current, and that gives you your 1 or your 0.
Yeah.
For our qubit, what is our globe? I'm assuming it's a particle.
It can be, for sure. So you have multiple options, and I think it is certainly much easier to have the arrow pointing somewhere on the globe in mind when thinking about a qubit.
Right.
But there are more physical ways that you can think about a qubit. For example, maybe your qubit is an individual photon, a particle of light, so the smallest amount of light that you can have at a particular frequency. And a photon has something called a polarization. So you can have, a photon is some oscillating electric and magnetic fields. And the electric field can be oscillating either vertically or horizontally. And it can also be doing other more exotic things, but for our purposes, we can just think of those two possibilities. So mapping over to the qubit, the vertical oscillation or the vertical polarization with the electric field swishing back and forth in the vertical direction, that could be called the up arrow state. So the state of the qubit with the arrow pointing directly at the North Pole. And then when the polarization is in the horizontal direction, so the electric field is oscillating left and right, that would be the qubit in the down arrow state, so with the arrow pointing down at the South Pole. So then you can ask the question, what is the equivalent of like a right arrow state, so with the arrow pointing somewhere along the equator? And that would be the electric field oscillating diagonally. So sort of a little bit in the vertical direction, a little bit in the horizontal direction.
Right. Okay.
That kind of thing. Okay, so that's one possibility. Another possibility is that you have an atom, or an ion, or something like that. So an ion is, an atom without an electron or with an extra electron, and the state of the qubit can be determined by the energy state of that electron, or basically you can kind of think of it as how far away that electron is from the nucleus of the atom.
Okay.
So just like before, we specified two states that were kind of special in the qubit, so the vertically up and down states. And you can construct a qubit basically whenever you have two special states that you can identify.
Okay.
So for example, with an electron, the electron can be sort of closer to the nucleus or further away. And those two states that the electron can be in can be thought of as the vertically up and down arrow states.
So I guess there are trade-offs and benefits to each of these. Do you have like a are there like, please tell me that there are like different camps that are just like, and like, oh, it's Bill, he's one of those photon cubic, like, is it like really petty and bitter like that?
Look, I think within the field of implementation, so people that are actually in the business of making a quantum computer, they all have their own methods, and they're all pretty... Or there's a reason that they are using the method that they're using.
Right.
So someone that is working on a trapped ion device, so using qubits that are made up of these atoms with or without an extra electron, they are convinced that their method is going to be the way in which we can actually build a full-scale quantum computer. And someone else in a different field obviously thinks differently.
Right.
I mean, I'm not within that world so to speak, so I'm more in the theoretical camp, in which I don't need to necessarily care too much about the advantages and drawbacks of each method. But there is a method of quantum computing that I am looking at, something to do with superconductors, which we might have time to talk about a bit later, or maybe in a different episode.
Yeah.
And, I think that those methods are quite interesting and quite promising, but they have unique challenges associated with them. So maybe that was a very diplomatic answer, but...
Oh, absolutely. I was hoping to get you on the record, and then like 20 years from now, when you're getting your Nobel Prize, I pull out this saucy audio and like,
Yeah.
No.
Me saying that photon quantum computers will never work.
You're right.
Something like that.
Yeah.
I know. I don't have any particularly strong opinions one way or the other.
But being more on the theoretical side, is it that the stuff that you study and develop could be applied, generally speaking, to like either or any of these methods, and it's just a matter of working out the particular kinks.
Yeah, there are certain things that I am looking at that could be applied to any type of quantum computer, but there are other methods techniques, and strategies that I'm interested in that are only really applicable to these superconducting qubits.
Mm-hmm.
And superconducting qubit is a term which is somewhat nebulous. So, in fact, I'm not looking at what many people talk about when they mean superconducting qubit. I'm looking at so-called topological superconductors. So that's a whole extra kettle of fish that I would be really interested to getting into at some later stage. But yeah, the stuff I'm mainly working on has to do with these topological superconductors, and that's a specific implementation of quantum computing.
Sorry to derail things. Trying to get a sound bite. No,
that's fine.
All right, so we have no matter what we have, right? We either have our photons or we have our ions, and they can give us something that is not necessarily 1 or 0. Or they could be, but not necessarily.
Exactly, yeah. So they could be a 1 or a 0, which, by the way, correspond to the down arrow and up arrow states.
Right.
We just call them 1 and 0 states because they're in analogy with the states from a classical computer.
Right.
But there's nothing particularly 1 or 0 about them.
Yeah.
And then they can be somewhere in between, which is to say, again, as I said before, that's not necessarily very mysterious when you think about this arrow pointing in 3-dimensional space.
Right.
We are familiar with arrows, obviously.
Yes.
But things do get a bit confusing and weird when we talk about measurement. So maybe we can discuss that now?
Sure.
So do you have any understanding of what that could be referring to in this context?
Yeah. So, well, let's see. So in the quantum realm, to sound like a YouTuber, in the quantum realm, you have your quantum stuff happening, and then I guess depending on your interpretation, because there's like 12 interpretations, it's like not until you measure something that you, again, to be like buzzwordy, you collapse the waveform and everything kind of picks one way to be. And so, or I guess this maps onto quantum computers, is you have your algorithm set up and then you let it run and do its thing, but you don't get the answer until you make that collapse happen with your observation. Or we can work there. We can work.
Yeah. But yeah. So going back to what you said before, that is one picture that you can have in mind, which is, to reiterate, the state of your qubit. For example, if you just have one qubit, is, as I said before, is an arrow pointing in space. It can be pointing anywhere, but when you make a measurement of that qubit, when you observe it, the state collapses to one of two possibilities. So, for example, they could be 0 or 1, up and down.
Mm-hmm.
I think that a nice way of thinking about measurement, which maybe perhaps takes a little bit of the mysteriousness or spookiness out of it somewhat, is it's a way of converting quantum information to classical information. So classical information we're thinking about as zeros and ones. So they are binary digits, the important part being that there is a finite set of possibilities.
Right.
And quantum information, the state of a qubit, is not finite. It can be pointing, the qubit can be pointing anywhere in space. That is a continuous possibility, continuous range of possibilities. So to convert between that continuum to the binary or to a finite set, you need to somehow restrict your information. You need to collapse that state.
Right.
You need to get rid of a lot of that information. And so that's what measurement does. Obviously, it's not, that's not the last word on the matter. In fact, it's an incredibly complicated topic that most people, I would say, don't really have a firm grasp of. And in fact, as a field, quantum mechanics takes measurement as a sort of given. It's something you add on top of an already existing set of postulates about quantum mechanics. So, for example, you could get rid of measurement as a postulate and you would have a perfectly natural, nice theory of how things evolve in time and interact with one another and things like that. But then we've got this strange feature of the world that, we measure something which looks normal, and then it jumps into one of two possibilities. And within the field of quantum computing, measurement produces an output of the computation. So like in classical computing, an output could be, the answer to a question, and it would be represented by a bunch of zeros and ones. Well, similarly, in quantum computing, the output that you want is the answer to a classical question. Like, what did I have for breakfast this morning, or something like that. And that would also be represented as a string of zeros and ones. So to achieve that, to get the answer to the question, we need to convert quantum information to classical information, and the way that we do that is by measuring. So measurement in a physical context can take all sorts of different forms, and it can be very complicated and difficult to understand. But basically, all we need to think about is the abstract mathematical stuff. And one way of conceptualizing that is by thinking of a measurement as a sort of this way, that way question.
Right, okay.
So a question that I could ask of a qubit for which I get one of two different answers. So for example, are you pointing up or down? That's a question I could ask of a qubit. And so if it's pointing up, it's obviously going to say, well, I'm pointing up. And if it's pointing down, vice versa, it says I'm pointing down. But what happens if it's pointing to the right, or pointing somewhere along the equator? And I say, where are you pointing? Are you pointing up or down? Well, it just picks an answer at random, and it jumps into that possibility. So to unpack that a little more, if I have a qubit that's pointing to the right, and I say, are you pointing up or down? There is no good answer to that question, but it still has to provide an answer to the question. So it picks at random. 50% of the time, it will produce the answer up, and 50% of the time it will produce the answer down. And then, after the measurement, it jumps into the state in which it said it was in. So it was initially pointing to the right, for example, and then after the measurement, it says I'm pointing up, and the state of the qubit changes because we've done the measurement to it. So it then, if you like, it rotates to now be pointing in the up direction. So there are these two features of measurement which are very, very strange. The first is that it's seemingly probabilistic. There's nothing that you can know about the system before you do the measurement which is going to tell you which measurement outcome you're going to get. It's purely random. The second feature is that measuring a system changes that system. So initially we start with the qubit with the arrow pointing to the right, and after the measurement we have a qubit with the arrow pointing up or down. So those are the sort of two take-home those are the two take-home features about measurement.
Yeah.
Or take-home messages. So yeah, what are your thoughts about that?
So I mean,
it's a bit weird.
Where it becomes a little fuzzy, right? Mm-hmm. Is it has this state that it is in. We need to convert it to something that we can use and understand. And so it necessarily has to choose something that it isn't. And that's, my pea brain tells me that would cause whatever the answer to be that you're trying to get to be wrong or incorrect. So, or not what you're looking for exactly.
Yeah, that's one of the sort of curious features about quantum computing, I think, is that despite the fact that seemingly it seems like this whole thing would be completely useless because the outputs that you get from your measurements are random. Mm-hmm. However, there are very clever ways in which you can perform these logic gates or sequences of logic gates that you can perform that mean that the answers that you get are very, very likely to be the answers that you are actually looking for. But basically, in the vast majority of practical cases, if you are doing a quantum algorithm and you want to find some answer to a question, you're not 100% certain that you're going to find that answer. You're just very confident that you will find that answer.
Okay.
But you might get an answer and you hopefully are able to check if it's the right answer. And then if you check and find it's wrong, then you just have to do the thing again.
Right.
And hope that you get the right answer next time.
Yeah. Yeah, I guess that's so I guess with a classical computer, assuming like your transistors are perfect and you never have error in that sense, like you are guaranteed to brute force what you're looking for. But with the quantum computer, it's more like is probably it, and we can kind of dial in our certainty, but it's kind of like you never know.
That's right.
Okay.
And in fact, in most cases, you might have some tolerance, some error tolerance that you have. So I want the correct answer with probability 99.9%, something like that.
Right.
Well, if I want that probability of success, then I have to perform an algorithm which is this long. And if I want the probability 99.99% of success, then I have to perform a longer algorithm. I need to do more gates. So I don't think that's universally the case, but that's certainly a paradigm that you could have in mind for how these quantum algorithms kind of work.
Right.
And yeah, usually when you're considering an algorithm, one of the things that you might consider is how does the length of the gate sequence that you need to apply, how does that depend on the success probability that you want?
Right.
So if the gate number blows up hugely as you increase the success probability, then maybe it's not a great algorithm.
Right.
Something like that.
Yeah.
Actually, can I maybe I could just jump back to something that you said right at the beginning. This is a very chaotically structured episode, evidently, but
not unlike quantum physics itself.
Absolutely. In fact, quantum chaos is a thing if you're into that kind of thing. But it's a field of research. Okay, so something that you said before, right at the beginning, which I was just reminded of now, was that there are certain problems that would take the lifetime of a human to perform on a supercomputer, or on a very good classical computer that we have at our disposal. And that's definitely true. However, the sorts of things that we might be interested in if we're in the field of quantum computing is not so much the absolute time it takes to solve a particular problem. It's about how does that time scale with the size of the problem. For example, if you take two really big numbers and multiply them together, that might take a short time or it might take a long time depending on how big the numbers are. However, from a quantum computing perspective, or just a computing perspective, that's an easy problem. No matter how long it takes, that's a really easy problem to solve, because the time it takes to do that problem doesn't grow particularly quickly with the size of the numbers that you're multiplying together.
Yeah.
So I'm not quite sure how quick it actually is, but I think maybe if you double the number of digits, you more or less double the time it takes to perform the multiplication. Maybe it's quadruple, something like that.
Right.
Doesn't really matter. All that matters is that if you think of the size of your problem, say the number of digits of the numbers you're wanting to multiply as n, so n some number that you can input, then the time it takes to perform the computation is some polynomial of n. And now it's very, very counterintuitive, but we think of, at least within the field of complexity, and in quantum computing, we're sort of interested in the way that these problems scale, so linearly or quadratically or exponentially. And then we say that basically if anything is a polynomial complexity, so if the time to solve the problem scales as some polynomial of the size of that problem, so n cubed or whatever, then that's easy. And it's counterintuitive because if you've ever seen the graph of like x to the 4 or x to the 10, it grows exceptionally quickly. It's very, very rapid. But from the point of view of complexity, that's easy. And the reason it's easy is because when compared to exponential growth, it doesn't even compare. It's just not close to being as fast as exponential growth. So if you can take a problem which, with the time that it takes to solve that problem, growing as e to the n, so exponential in the size of the problem, and you can reduce that to some polynomial, then that's a qualitative change.
Right.
It's huge. It's amazing. But if you take something that grows as x cubed or n cubed, and you reduce it to n squared, well, I don't know, maybe we're not so interested in
Right.
Now, in practice, of course you are interested, but from a theoretical point of view, you only really care about how these things scale and whether they're polynomial or exponential or something else.
Right.
And I should be clear about what I mean by theoretically. I guess there are sort of two different perspectives that you can have on this question. One comes from the study of quantum algorithms, and in this kind of theoretical framework, one does care about sort of polynomial differences, so between n squared or n cubed or whatever.
Right.
But in the field of complexity theory, for example, we only care about whether or not the algorithm is polynomial or exponential or something else. And there's much more to say on complexity theory. It's not anywhere near as simple as that, but that's a useful starting point. And also, there's some reason to believe that if your quantum algorithm only gives you a polynomial speed up from the best known classical algorithm, so the best known classical algorithm scales as something like n cubed, and the quantum algorithm scales as some smaller polynomial. It's possible. I mean, some people argue that in practice that is not actually going to be useful when actually implemented. In order to sort of overcome the really, really large overheads that a quantum computer comes with, the really big difficulty of actually building a quantum computer and running an algorithm on it, in order to overcome that, you need an exponential speed up to make it worthwhile. But that's I don't know if that's universally accepted. It's something that people argue, though.
And so, do you have? I mean, like, I hate to be the guy that's like, well, so then what are some practical? Because like that's not what it's always about.
That's fair. Absolutely.
I want to be on the record as not being one of those people, though, because I think that sometimes it's just cool to do cool things. That said, like, what are some other, or do you not even touch that realm? You don't even have like a casual relationship with the practical applications, or maybe you do.
So I would say I have a casual relationship with the applications, and in certain types of application, I have a somewhat closer or more intimate relationship with them. But generally speaking, it's not part of my research. But I can definitely talk a little bit about it. So the flagship application, which is actually not very useful, is factoring large numbers. So before I mentioned you can take two really, really large numbers and multiply them together. You get an output very, very quickly. However, going in the reverse, if I take a huge number and I want to find the prime factors, sometimes that's easy. Maybe the prime factors are 2 and 3 and that's it. And you just multiply them together a bunch of times. So that would be nice. But it could take a huge amount of time. And the point is that the time it takes to perform this task grows exponentially in the size of the number that you're trying to factor. A little while ago, I was kind of curious, and I took two massive 150-digit numbers and multiplied them together, and they're prime numbers. So if I multiply them together, then the number that they produce is only going to have two factors, which are these two prime numbers. And I was looking up how long it would take to factor that number if you didn't know its prime factors. I couldn't find a definitive answer, but it was about 300 digits, maybe 314 digits. And from what I could tell, it would have taken a supercomputer at minimum about 10,000 years. So that's a huge, huge amount of time. And as I said before, it doesn't really matter the actual amount of time; it just matters about the scaling. But it's kind of interesting to note about that.
And again, this is mostly like a problem for like encryption and
yes. So there are certain cryptographic protocols, so protocols for securing information that I want to share between maybe me and you. Maybe we're sending WhatsApp messages and I want to encrypt those messages so that some third party can't read them. One way of doing that is to use what's called RSA, the RSA protocol. And that's difficult to crack because it relies on the difficulty of factoring really large numbers.
Right.
Basically. So if you had a quantum computer, and I didn't say this before, but a quantum computer can factor that 314-digit number much, much more quickly. And if I was able to do that, if I had access to a quantum computer, then RSA would no longer be a very good protocol to use, because I could hack it very easily.
Right.
The reason I say it's not very useful is because there are a whole bunch of cryptographic protocols that you can implement that don't rely on the fact that it's difficult to factor a large number. So just use one of those instead. But it is interesting that there is this thing that quantum computers can do that classical ones can't, and it's it kind of started the field of, well, at least the great interest in quantum computing and quantum algorithms.
In keeping with our chaotic jumping around, so I think I want to just nail down where the quickness comes from.
Yeah, it's tricky. And I think, in fact, at the heart of it, it's not very clear where the speed up actually comes from at the end of the day. We know that there are ingredients that you need for a quantum algorithm to be better than its classical counterpart. Maybe a better way of thinking about this is you've got some quantum algorithm and it does its thing, produces an output, and what you want to know is how hard would it be for a classical computer to perform that algorithm or simulate that algorithm? How hard would a classical computer have to work to give you the same output with the same probabilities as a quantum computer? That's kind of the same thing as saying, is this quantum algorithm doing something that a classical computer can't? And so there are many different ways of answering that question. Where do you think the speed up comes from? You sort of mentioned this.
Yeah, so I guess, my hunch tells me that, if your arrow on the globe is not pointing directly up or not pointing directly at the horizon, right? But let's say it's like 1 degree above the horizon, right?
Above the equator.
Above the equator, yeah. My hunch tells me that at that point, it would not necessarily be 50-50 where it would...
Ah, right. So that's a good point. So the closer the arrow is to the North Pole, the more likely you are to measure that outcome. And vice versa, if it's closer to the South Pole, you're more likely to measure that outcome. So it's only 50-50 when it's on the equator. Okay.
Yeah. And so,
so go.
Oh, no. So, so that's where my intuition is going, where a classical computer would have to, this is going to be a really extended analogy or metaphor now, but a classical computer would have to be like, all right, well, let's take every possible one. We gotta do that, right? And for those that are listening, I'm making pizza slice sectors with my hand right now.
So you, to simulate it, you would kind of need to discretize your sphere, and then one way that you could do a simulation would be to break your sphere up into a bunch of pizza slices, as you say, or a bunch of segments going from the center to the surface, and that would be the way that you would represent your qubit's state classically. You would say, well, if it's in this segment, then I assign it this bit string. If it's in this one, I assign it this bit string, etc. And then each of those has some probability for producing X measurement outcome if I were to measure it. So that's certainly one way that you could do it. There are probably better ways that you could simulate the measurement of a qubit. So the way that we might think of where the quantum speedup comes from could be a little more abstract. So certainly one way of thinking about it could be, okay, you've got a qubit with a continuous array of possibilities, but and also as you add more qubits, the dimensionality of the space of possibilities grows exponentially. So what I mean by that is that the storage that you need to simulate or store that state classically grows exponentially. But it's not necessarily the case that just because you have some exponentially growing storage space, that means that every algorithm that you do on n qubits is going to be really hard to simulate. And the reason is because there are some algorithms that are just going to be really easy to simulate. You could even just do it in your head. For example, I give you n qubits in all pointing up, and you do nothing to them, and then you measure them, and obviously they're all going to point up. So that's a very trivial example of something that would be very easy to simulate on a classical computer without storing the states in any particularly fancy way. Okay, so some other answers could be, well, a key ingredient that you need to make a computation difficult to simulate on a classical computer is entanglement. So we haven't talked about that yet, but it's a really important aspect of quantum computing. It's sort of needed to make the computation do anything useful, make it difficult to simulate classically. We won't go maybe as much into depth on what entanglement is this episode because it's a whole other kettle of fish.
Yeah. It's for all the noobs out there. No. So yeah, my brief understanding of entanglement is this is referring to the spooky action at a distance that Einstein talked about, and it's you have two particles, one is spin up, the other is spin down, and but you maybe don't know which is which, and they can be on the opposite ends of the universe. And as soon as you look at the one over here, and it's spin down, you automatically know the other one over there is spin up, despite the fact that they are very far.
That's exactly right. Yeah, and
I know something.
So that's
woo, yeah, cool.
Yeah, absolutely. So that's the heart of it. But there is much more to say about it, obviously. For example, I could ask, are you pointing up or down to one of them? And I will, if it provides the answer up, then I will know that the other one is now going to be pointing down. But I could also ask, are you pointing left or right? And again, these answers are going to be opposite, no matter what happens. So you have this perfect anti-correlation. So whatever answer you get in on one particle or one qubit, you'll get the opposite answer in the other qubit. So that's a very strange feature, and it's not necessarily obvious why that's a strange feature. For example, if people have an example of someone who always wears odd paired socks. They just reach into their drawer and take out a sock at random, and if it's the same, they're like, it's boring, I'm gonna throw that out. And so if you see this man walking through the door and he's wearing a blue sock on his right foot, well, you can bet when his left foot comes through the door, it'll be clad in a red sock or something like that.
Right.
So, but that's not very quantum. So why is quantum entanglement not the same as this spooky sock stuff? That's a sort of difficult question in and of itself to answer briefly, but there is a reason, and it has to do with the fact that you have this perfect anti-correlation. No matter which question you ask, they're always going to be producing the opposite result. It's very strange, very, very interesting, and there's a lot of continuous study on entanglement within the field. Okay, so that's one ingredient that you need for a quantum computer to be difficult to simulate, entanglement. But it's not the case that if you have entanglement, then your quantum algorithm will be difficult to simulate. It's unfortunately not that simple. In fact, I can give you remember we were talking about gate sets before? I can give you a set of quantum logic gates that can produce very, very entangled states. And yet, it's very easy to simulate. I can do a whole bunch of these gates on some input state. So the input state is kind of important. The state needs to be, for example, all of the qubits pointing up. So, and then I do these gates on the input state, do some measurements, and I can determine the outcomes of those measurements or the probabilities of those measurement outcomes very easily. So you need not just entanglement, but you also need something else. And more or less that something else is kind of like a small rotation. So a rotation of my qubit from pointing up to pointing diagonally 45 degrees. So, I don't know, pointing somewhere in Europe, for example, or somewhere in North America. It's still not the case that if I just have these two ingredients, then it's definitely going to be difficult to simulate. It's much more complicated than that, but these are two kind of necessary ingredients. So some sort of small rotation of my qubit state, of my qubit arrow, and some entanglement, and that's yeah.
And
those are
like what it boils down to is that is just a physical limitation to, like, again, just going back to the idea of your transistor really only has it's got current or it doesn't. But this, when you get to your qubit, you have that added discrete, or there's just
continuousness.
That I mean, it is range. You just have range where you don't have in your transistor, and I could see where that becomes difficult to represent.
Yeah. So it's such a complicated question. What makes quantum computers tick? Why are they so powerful? But you have that small rotation or smallish rotation. There's no analog in terms of classical states, and so that is kind of exploiting the quantum nature of the qubit. And similarly, entanglement has no classical analog. There's nothing that's like entanglement in the classical world. And so it's kind of not surprising that if you have entanglement, you might be able to do more stuff than if you don't. Well, maybe this is a good place to wrap up.
Yeah. Well, I feel like I know a little bit more, as I always do when I have these conversations with you. I feel like I know a little bit more. It's gonna be you're as I always say, you're like 7-8 hours ahead of me. Just give me 7 or 8 hours, and then I'll have it all to let it sit in my head a little bit.
That's right.
It's just always fascinating, and I'm just gonna be thinking about this the rest of the week. We have plenty of areas where we can. I'm like, ever since you've mentioned topological superconducting quantum computers, I'm like, that is the name of my band now, and 2, I gotta hear more about that. So we will save that for another time.
Fantastic! I'm looking forward to it.
What does it even mean? What does it even mean? That's how I always end up.
Another time? What is that?
Yeah.
What is time?
Exactly? Yeah. But no, thank you, Campbell, as always.
Thank you, Brian, for asking the questions, and we will see you next time.
Have a good one, everybody. And if you need any more information, check the description. Send us your questions. We're going to get to your questions real soon. We have some.
We're sort of pre-recording these, so we're not sure when they're going to go out, but they will. And when they do, we'll be fielding all of your questions.
All of them here in the question field.
You've been listening to Question Field. Question Field is a Gain Media production and is produced by its hosts Campbell McLaughlin and Brian Buchanan. For more information, please check us out on Instagram at QuestionFieldPod, on Twitter at QuestFieldPod, and on TikTok at QuestionField. If you have a question you'd like to submit, or would simply like to leave a message, please send us an email at questionfieldpod@gmail.com. Recently, the James Webb Telescope discovered 5 new stars located in the review section of your favorite podcast app. Thank you for listening.